very interesting topic in the food, energy, and water system. Over the past few months, the Center for Cyber-Physical Food, Energy, and Water Systems have initiated a series of webinars to increase knowledge and foster expertise in different aspects of the food, energy, and water system. And today we have the privilege of receiving Professor Rudolph, who would be taking us on another aspect in the food, energy, and water system. So please permit me briefly to read the biography of Professor Rudolph while I invite him to start his presentation. Please confirm if you can hear me, colleagues.
Yes, I can hear you.
Yes, we can. Can hear you. Thank you very much. So I will now take the biography of Professor Rudolph. Professor Rudolph Oosthuizen's distinguished career began with his enlistment in the South African Air Force in 1990, where he earned a engineering degree in electrical engineering in 1994, an honors degree in industrial engineering in 1998, and a master's in engineering management in the year 2002 from the University of Pretoria. He specialized in system engineering in the Air Force, focusing on electronic warfare and command and control. In 2008, Professor Rudolph transitioned to the Defense, Peace, Safety, and Security Division at the Council for Scientific and Industrial Research, the CSIR, as a senior systems engineer. There, he supported various command and control projects, leveraging his expertise in systems engineering. He earned his PhD in engineering management from University of Pretoria in 2015, concentrating on modeling command and control systems for requirements, capture, and concept development. Using model-based systems engineering practices, his research emphasized the human elements in socio-technical systems, particularly cognitive and human factors. Professor Rudolph focused on integrating data science and artificial intelligence to support decision-making and modeling of complex situations. In April 2023, he was appointed Associate Professor at the Graduate School of Technology Management at the University of Pretoria, where he teaches systems engineering and systems thinking. His current work applies systems thinking and systems dynamics modeling to analyze how policy decisions shape just energy transitions, including feedback effects, unintended consequences, distributional impacts, and pathway trade-offs across technical, economic, and social domains. He is a registered professional engineer with EXA and a certified systems engineering professional, INCOSE, with more than 20 years of experience in conceptual systems modeling. Colleagues, please welcome Professor Rudolph.
Welcome, Prof. You're welcome, Prof.
Okay, thank you. Good morning, everybody. I think I'm going to share my screen. Let's figure this out again. Every time a trick. Okay, and let me see. Okay, do you see it in presentation mode?
Yes, please. You can see your screen, Prof.
Okay, good. Thank you very much for inviting me. I think it's a great honor. Once I got the invite, I read some up about your center there. It's quite impressive what you people do. And there's some quite esteemed researchers there in your field. So I hope I am up to scratch for you people. Maybe before I start, let me quickly ask, what is the level of knowledge on specifically systems thinking from the audience. Who of you know systems thinking well? Can we just show of hands, please, if you do? And have anybody done system dynamics modeling? Or have experience in system dynamics modeling? Okay. Okay. Namdi, okay, you got some. Okay, good. Okay, I hope I don't bore you. I'm going to go a bit of a detail, some of the basics. And Anthony. Okay, that's good to know. We need people for our society to get involved in South African System Dynamics Society. But we can chat about that afterwards. Okay, you got the invite. I'm from the Graduate School of Technology Management at University of Pretoria. Maybe just a few words around that. We are a postgraduate school under the engineering, built environment and IT faculty. So we are a separate school from engineering and IT and built environment. We are only postgraduate. We only teach honors and master's degrees in engineering management, project management, and technology management. Engineering management, you can roughly describe it as an MBA for engineers. So we have many of our students are part-time, we are only part-time, and they're all coming from industry with experience, and we have actually very interesting classes with people with that much industry experience, and many, the average age of our students at master's level is about 34. So we also learn a lot from them. And secondly, as you've heard from the CV, I am a young academic. I've only been involved in academia for the last 5-6 years. So I am still learning about academia, but I come from industry with some experience. Hopefully that helps me. Good. Let's see if I can click there. And yes. So, okay, so my talk is mostly around systems thinking, system dynamics, and how that can help you address your issues that you want to address in your food, energy, water nexus. Viewing it as a complex problem. So in my talk, I will first talk about the basics first. What is a system? Why do you want to talk about things as a system? Then going into complexity, and because we want to have our energy nexus to be resilient, and what is resilience and what does that mean? Then I'm going to delve deeper into systems thinking, how to address these complex problems, look into the fundamentals, and I'm going to briefly discuss a few tools and approaches that I like to apply. And then I will bring it all together to see where AI supports the systems thinking process, and also focusing on how it can be beneficial to the food, energy, water nexus. Good. I'm going to use this to go down. Right. So what is a system? There are many definitions of systems. Every field's got its own definition of system. Myself being a part of INCOSE standing for the International Council on Systems Engineering, their formal definition is that it's an arrangement of parts or elements that together exhibit behavior or meaning that the individual constitutions does not do for you. Your system can be either physical or conceptual, or a combination of both, and it consists of matter, energy, and information that results in observable behavior of your system. So the main ideas that we look at here, first of all, a system has entities. They are connected and interrelated and influencing each other. And these relationships enable your system to provide behavior, or what you like to talk in engineering is you want to achieve a function. And often this function is more powerful than a sum of the function of the parts. You want the emergence coming out of it, but we'll get to emergence a bit better later, a bit deeper. So just describing this a bit deeper, I'm going to activate the cursor here. laser pointer. Okay, so the system, as I said, consists mostly of elements that are connected and sitting within a boundary. So these elements can be anything that you want it to be. It can be physical, it can be hardware, software, a machine, that can be services, processes, techniques they want to have. It can be people, social elements, a soccer team, a rugby team, an organization, a work environment. That can be, your system can be shown as information, as you look in software development, and also your system can have economic, biological, and other political type elements that are making things very complex. The second important part is that these are the relationships between them. This is how they interact to each other, and where a change in one element might cause a change in another element, and that's an important aspect to consider. And also you have a boundary around your system, and often this is the most difficult thing to get right, because you can pick where you put the boundary out of your system, and that is determined by the what you want to achieve with it. And in engineering, a system has also a life cycle, and it often have a purpose. We design a system for a purpose. So firstly, look at the elements of a system. The system is actually a mental construct. You can decide what you want to define as a system. A system can be from something as small as a molecule. I can describe a molecule as a system. It consists of atoms, electrons, protons, etc., and the interrelationships between them are the forces they have, and that result in certain characteristics that occur. And you can describe anything as a system in between, up to the whole universe can be described as a system. We also use the term a holon, where a holon is a whole in itself, a system that is a whole, but it also is part of a larger system. So, and that can be structured in a hierarchy, what we like to call a holarchy. And so you pick where you want to put your system in a hierarchy, and where you put your boundaries, and what the level of abstraction you want to work at. This is normally determined by your level of abstraction and your level of focus that you want to investigate and address. And I think this is also one of the most important decisions when doing systems thinking. Where do you want to work? Secondly, you have your interconnections. These are the structural element that enable the system elements to interact with each other. There can be physical connections, there can be information flows, institutional dependencies, there can be laws, anything where one element influences another element. And exchanges of information, energy, or material can occur through those interfaces as well. And they determine how change from one element can propagate throughout your system. And there's a nice picture about looking at the food, energy, water nexus. Then looking at the boundaries, and I think this is also a very important decision that you want to have to make when you address a problem. You need to decide, what are you going to focus on? What is the core system that you're going to address or analyze? What do you leave out and why? And what influence does those external elements that you don't focus on right now have an impact on you? A second person may have a different layer. They might be focusing on a higher level system, including things around it, influencing on your system elements. And the key thing here is, once you pick your layer, your boundary, you know why, what you excluded and why, and what influences of the exclusions will have on possible decisions you are going to make. And this is part of your assumptions. And always help to do a proper critique of where you pick your boundaries. Don't you miss something? Don't you miss a stakeholder or an influence that is actually part of your system? And this is something that also evolve as you go through the process, as I will show later, where you pick your exact layer. Good principle often is to start narrow understand things and then expand as you start learning about your system. Okay, and then one of my favorite topics is complexity. I'm also part of a complex systems working group within INCOSE where we try to understand what is complexity, and there are many different definitions. Sadly, even within an organization like INCOSE, we don't always agree on what is a definition of complexity. However, the word derives from the Latin word plexus, which means braided or entwined. That means that the elements in your system are so tightly intertwined with a very high interconnectivity that is very difficult to understand a system if you take the things apart. If you take it apart, the things don't behave as they used to, as they should. So reductionist methods don't necessarily work to address complexity. You have to look holistically at the system as a whole. So it doesn't help decomposing your system into individual elements to try and understand how each work, or from that derive how the system as a whole work. You have to look at the system as a whole. However, this doesn't mean that reductionism is wrong. It's necessary, but it's not the only way to address it. You have to take your system apart to see where the interconnections are, and then to analyze them and put them together and synthesize the system to make sure you understand the system as a whole also. You have to look at it at different levels. So what is a complex system? There are many frameworks, but we reduce it to this very basic one. You can either look at simple, complicated, or complex systems. The simple system is something that you can easily predict the behavior of your system. A good example here is something like a motorbike or a bicycle or a simple old car with a old technology type engine in it. Most people know exactly how the car works, and if there's something wrong with it, a good mechanic will very quickly fix it and what part to replace. However, if you add more parts with many more relationships, it might be a bit more difficult to analyze your system. It can be like a electrical car or the self-driving cars. No, let's leave the self-driving cars out of this. That might come into complexity. But a car or an aircraft is a very good example of this. You might need to do a bit more work and analysis to find the error, but you can do it. There is reasonable certainty between cause and effect, and you can address the problem and you can get a good solution and get it fixed up. However, in complexity, there you have insufficient certainty between cause and effect. There's unpredictable behavior. You don't understand it. You don't understand the system as a whole. You know you don't have enough information to understand the system as a whole. So you have to do process and steps and apply tools to get a better understanding of it. So how I like to look at it, the difference between complicated and complex is where your aircraft is a complicated system, your aviation industry or a air force can become a complex system where you cannot really predict with certainty into the future exactly what's going to happen. There are many examples looking only at the aviation industry, things like what is the impact of the war in Iran on aviation around the Middle East. Also, there was in the past these volcano eruptions that put ash over Europe, and that also had a big impact on how the aviation industry behaved and how it affected flights, how it affected prices, etc. So how we like to look at it is within a complicated system, your parts are known. There are many of them, but they can be figured out. There are known rules and you can solve it and you can get a solution to it. However, with a complex problem is that there's very interconnected. There's lots of uncertainty and you must require adaptation. So complexity needs to be navigated. It cannot really be resolved. One thing that we have developed as a part of the working group is another framework, continuing on this, where we try to see where we work with the system. So there we have the intricacy of your system, that meaning the amount of elements and their relationships. That's only one dimension of complexity. And then there are confounding factors. That includes your understanding, risk, uh, time limits on you, resource limits. That makes it too difficult to quickly or limit the amount of time you have available to resolve your system. And in the industrial age mindset, we worked with everything in this area. We either had a complex or complicated system, and then it was something we have your tractable complexity. If we think we have a complex system, we apply some tools, we get some experience, we get some learning, and then we understand it, and then we drag it back to it being a more complicated system. This is typically what we do in something like systems engineering. We, through modeling and engineering approaches and risk management approaches, we bring them back to complicated levels so that we can design a new aircraft or a new power distribution or electricity reticulation system to solve the problems of the country, or to build a new dam or something like that. However, there is a threshold of complexity where you cannot do that anymore. Then you have different approaches to address with complexity, being more resilient, being more flexible and adaptable to adjust to what is going to happen within your system. So one must know where you work and what tools you can apply within each area. So typically, in your engineering design approaches, they work in this environment. Systems engineering works in that environment. And then when you don't have that certainty, you apply systems thinking type approaches, where you have to learn a lot more about the system before you can do anything about it to improve the situation. So just a final thing on complex systems is we must address the system as a whole, not piecemeal way. And it takes time and effort and a lot of learning about the system to achieve this. And then a very important aspect is problems cannot be solved, complex problems, because once you get a solution, the problem is changing. There's new factors coming in. Your solution that you implement might have unintended consequences in other places within your system, and you must continually adapt to that. So you influence your system than solve it. And Donella Meadows, one of the big gurus and writers on systems thinking, used to say, you dance with the system. So you have to keep learning about the system and to see how it adjusts and adapts over time to keep implementing new measures to steer it in the right direction for you. Maybe just a point on this stage. Why are we concerned about systems? When we have a complex situation, call it like that, a problem, when we can describe that complex situation as a system, then we can start applying tools to better learn about it and understand it. So that's where the systems aspect coming in. It empowers us to address complexity. Another characteristic of complex systems is emergence. Emergence is like what you see from birds flocking, in nature, termite mounds, weather patterns, traffic behavior patterns. That is when elements within a system interact at local level with very basic rules, but that leads to global behavior that is not as expected and is actually quite interesting. And it comes as a surprise to the observer. Looking at birds flying individually, you cannot think or comprehend that they will start behaving like that when a big flock gets together. And this emergence can be intended or unintended. The being engineer, when you design a system, when you design a jet engine, there is intended emergence of thrust and heat, and the unintended consequences are noise. and maybe other vibrations and stuff within it. So you design something with your intent behavior in mind through engineering. However, that also can lead to unintended consequences. And this behavior can sometimes be a surprise to the observer because it was an unknown to them, if you can go and look at that direction as well. And it can only be assessed and measured when you look at the system as a whole with all the elements together. And you cannot reductionist approach derive this because you just look at, for instance, a bird in isolation. So therefore, and they also included example here of the food energy water nexus, where they are actually influencing each other. And that might lead to emergence of a system. Emergence that you want in something like a food, energy, water system is you want a resilient system and you want food security. That is the behavior that you want. However, that might not always happen because life happens and nature happens, and your good ideas and good policies might not achieve what you want them to achieve. So for this is where you apply systems thinking to get a better understanding and to get an not necessarily predict, but learn about what possible behaviors can occur when you do stuff within your system. As I said here, you want a resilient system. So what is resilience? Very important to understand as well. That is the capacity to anticipate, absorb, recover, adapt to, and where necessary, transform in response to disturbance. So it is a lot more than just returning to your original state after your disturbance, because that original state might not be optimal, it might not be sustainable. So from a disturbance, you must be able to adapt. Look what happened after COVID. After COVID, we didn't all just go back to working full-time anymore. There's a lot of things that have changed. There's lots of places that works online, although many of the work environments bring them back to offices, but it made a lot more things possible for happening online. And we still see that today, like this briefing today here. Otherwise, I had to drive all the way out to Johannesburg from Pretoria to be able to speak to you guys. And resilience is a very good example of emergent capacity. And it also depends on how your system is structured. Do your system have the flexibility to be resilient in adapting to changes? And your objective is not to prevent disturbances, because you cannot prevent all disturbances in a complex system. The system being complex, meaning you don't know about what disturbances can happen. So you have to be ready for the things you don't know can happen within your system. So that's why you apply and look at it through the systems lens, or apply systems approaches. So coming to this point, so now we say systems thinking is the solution to everything and every problem you can have. But what is systems thinking all about? So as I've alluded up to now, just as a summary of this slide, is to show that we can apply systems thinking to complex problems. When do you do that? Often you have solutions, but they don't seem to work. You're trying solutions to your system, but there's nothing taking place, or it's taking place too slow. Or sometimes your solutions that you implement only work for a short while, but then there's other problems popping up everywhere else in your system. And the same problem that you think you solved is also coming back after a while. And your past solutions don't remove the problem. Your past solutions are actually causing more problems to you. And you have many variables with cause and effect, relationships, and feedback within a system. So we apply systems thinking to simplify complexity through modeling, to try and understand the structure of the system, and to understand why is things happening within your system, the behavior that is observable around us. So the definition of systems thinking, again, there's no standard definition for it. It's not like for INCOSE, you have a definition for systems engineering, or there's a standard for ISO 1528 for systems engineering, but there's no such thing for systems thinking. The main reason is it has developed over time through different disciplines, and it's applied in many disciplines. But the one definition I like is that systems thinking is a systems of thinking about systems. It's a whole conglomeration of tools and methodologies that is suited within a philosophy and a set of tools to help you understand the behavior of complex dynamic systems. There are many methodologies that have been developed over time, things like a soft systems method, systems thinking, design thinking, systems engineering. They all are built on systems thinking. So let's look at how to do that. Also, there is not a standard process for systems thinking as like an ISO standard for it. So the process that I like is actually very simple, a very high level, and it needs to be adapted to whatever context you apply. You start off with framing your problem to clarify what are the challenges you want to address. You go and look where your boundaries lie and what are the key questions you want to answer within this complex problem you have. Then you start analyzing it and identify the elements and their relationships to do the systems mapping. For me, this is often one of the most important parts to the process, to understand your system. What is causing what in your system? What are all the elements within your system? Having done that, mapping it out, you start learning about it. Then you can go and look where is those feedbacks in your system that's causing the problems and the delays causing the problems. The unintended consequences that occur, to understand what is the structure that caused the observed behavior. Having done that, you can start designing your intervention. Here you can apply simulation tools to see if you want to develop new policy for a government level type problem that you want to investigate. What impact will that policy have on the system as a whole? And then you implement it, you apply it, and then very important, you have to monitor it because the problem don't just go away. Things happen and things change, and you reassess, was your definition of the problem right? Was you actually solving the right problem? And you do it iteratively. Systems thinking is a never-ending process. And one of the most important parts of it is you in the middle of the system that continuously learn about the system. Every time you apply one of these steps, you learn about the system, and you can have iterative feedback loops. As you're mapping the system, you can figure out, no, I don't have all the boundaries correct. Maybe I have to adapt my boundary, and you can do that a few cycles, and then you can go to the analysis, and this can lead back feedback loops to your previous steps to better understand and grow your understanding of the system as you go around it. So the key thing of this systems thinking process is your problem that you view as a system, you learn about, to understand the behavior you observe, and to try and steer it in the right direction. So let's look at the tools. There are many tools, and this is just a short list of it that is applied within the field. Iceberg model, rich pictures. I am just going to quickly visit a few of them. I'm going to talk quickly about rich pictures, systemograms, causal loop diagrams, and then your system dynamics, which is actually your stock and flow diagrams. I'm just going to visit them each quickly, just as a background to see how you go through the process to understand your system better. Okay, so I just have one slide on rich pictures. I think that is the simplest approach you can do, a simplest tool that you can apply. That is where you take your stakeholders, especially in the first part. That is where it's most important to understand what is actually the problem that you want trying to solve. Where your stakeholders get together around the board, draw pictures on a flip chart or on a big chart, to show where they are, what are the things that are bothering them, and what is the behavior that's causing the problems from their perspectives. The key thing is you want the mental models of all your stakeholders captured. Once you have that, you can start identifying your system elements and to get a rough idea of where they sit and how they interact. But that is just a starting point. So rich pictures is mostly applied within this step here and maybe progressing a bit to the rest. Sorry. Then, one of my favorite tools is the systemigram. Systemigrams and rich pictures are closely related, although systemigram is a bit more formal. You don't use freehand drawings. You can do that as one person on its own. You have a tool to do this with. So it can help you to frame your problem, but hopefully you've already done that in the beginning using a rich picture or something. But it focuses on mapping the system, identifying which are the elements and which are the interfaces, and you can start identifying some of the loops, feedback loops that occur within your system. So, but this is a more valuable just as your system mapping step. It was developed by Boardman and Saucer. This is in the realm of systems engineering, but its main purpose is to take the story, the narrative, or the information that you have around your problem in the system and capture that graphically and showing it in terms of elements and interfaces and the relationships between them. So this is a systemigram about systemigrams. And you read it like a story, and I will go through it quickly. So you have your system of interest or your problem or something that you want to improve or achieve is viewed by an observer who creates a narrative description, which is used to draw a systemigram, which is shown to your stakeholders to have an improved understanding and enabling a system of interest improvement. So that is the main storyline, but there's things that influence it. There can be documents. So your information about it is captured in documents that the observer use to create the narrative, which is the source of your nodes and also source of your relationships. The relationships is the connection between the nodes, and those nodes are plotted on a systemigram. And the observer also can use and identify and adapt your boundary, which help you to better understand your system of interest if you want to improve your systemigram. Your systemigram is shown to your stakeholders, which result in communication, which results in feedback, can be used to improve your systemigram or maybe adjust and adapt your boundaries, which will lead to a different range of nodes and relationships to be added to your systemigram. So this is a systemigram about a systemigram. As you can see, relationship to rich pictures, it's a bit more formal, but it can help you to get a better understanding of a problem, to see what information is there and what is the high-level structure of your system. So just shortly, it consists of nodes. Those are the principal entities in your system. As you have your narrative, you ideally like to have it like a story in text. When you have the text, you look for those nouns and noun phrases that are important within your system. You can list them, you can identify them, and these are typically your actors, capabilities, or artifacts within the system. And also you can look at your arcs. Those are the verbs between those nouns. And you can literally convert text into a diagram like this to tell the whole story. And the directions arrows show what is it, which nodes connect to which nodes. And it provides a visual account of the stakeholder roles and that can support you discussing your system with your stakeholders. It's quite easy to understand. And to arrange them into a structure, you can have a mainstay. A mainstay is the main storyline running through your diagram, and the other nodes are often just supporting or influencing the storyline that you get. And there are guidelines to it. You'd say typically 15 to 20 nodes, fits on one page. Your starting point often is your system of interest must be on the top left, and your end point must be the bottom right, which is the purpose of the goal you want to achieve. Once you have drawn the systemogram, it's very important that you don't cross lines and arrows. And that involves you to play around with it, especially people like me that got OCD. You can play around with it quite a lot, the whole day with a simple diagram to get it optimized, not optimized, clean and neat. And while doing this, you really ask questions about your system. If there is a connection between two nodes, is that connection really there? Is that the real connection, or is a connection via other connections as well? And you can simplify your story doing that. And this helps you to better understand your system. If you ask these difficult questions, move things around, you really learn about the system in the ways that you don't really see before the time. Okay, here is an example of a systemogram. This one is a bit busy. It's about project management versus systems engineering, project management systems engineering, and the problems they have. This one is a bit busy, but I've done that as part of a paper a few years back. As you can see, the nodes and the connections between them. And you can then focus on certain areas if you want to better understand certain themes within your system. This is one we did an example for load shedding in the winelands, what the effect of additional or alternative power sources will have on the system as a whole. Okay, and then once you have your systems mapping, you can start looking at your causal loop diagrams, where your causal loop diagrams focus more on your feedback analysis. Yes, some people just start at the causal loop without looking at the other things, the other steps where they identify the nodes, but the causal loop is a special case of the systemogram. Not all your interactions in your systemogram are causal, and not all of them are variables that can have causal relationships. So you focusing on those specific ones to draw your causal loop diagram, where you can identify what are your feedback loops, what type of feedback loops they are. And already by drawing a good causal loop diagram, you can start seeing where's your leverage points. And what are the loops that can determine what you can achieve or what you cannot achieve. So going a bit into causal loops, it is not as easy as it seems. It takes a bit of exercise to get it really right, but it focuses on the cause and effect behavior within your system. So you look at the directional cause and effect relationships where a change in a variable causes a change in another variable, all else being equal. We talk about the ceteris paribus principle. And that relationship or that influence can be explained through a plausible mechanism that operates over time. For instance, here you can say, if your stress goes up, you can consume more alcohol because you go out with your mates after work, you talk about your stress, and you have a few beers. And having that, that increase, but drinking a bit more alcohol reduces stress because you are relaxing, you're sharing your problems with your friends, and this is a balancing loop that you have there, and you can build up the whole system working through that. And every link also is not necessarily, well, preferably it is founded or supported by data, but often it is an hypothesis, what you think happens, what is in your mind, the mental models of your stakeholders support this. What is the cause of what, and what will be caused by something changing? And also you look at the continuous influence over time. So this can happen. It just doesn't only happen once. Every time you do it, it occurs. Okay, so it starts by identifying the variables. The variables must be something that can go up or down, something that you can measure. Investment can go up or down, productivity can go up or down, or resources or resource constraints can go up or down. So if there's a relationship between two variables, it is in the same direction, meaning that this one, if this one goes up, then that one will go up as well. If investment go up, your productivity, all things being equal, will go up. That's a positive relationship. Meaning that if your investment goes down, your productivity will go down as well because you don't have the right tools anymore. Careful, positive relationship does not mean good, or negative does not mean bad. It is just the direction of the change. Where your negative relationship means the change is in the opposite direction. Many conventions of causal loops actually use an O and an S to be more clear about this, opposite or same direction change. Where if your constraints increase, your productivity will go down. If your constraints decrease, your productivity will go up. So you go through your diagram, you identify all your variables that can go up or down, identify relationships between them, and you look at every one in isolation and you build all those links. Once you've done that, you start looking at loops. Loop happens when you have a closed sequence of errors that folds back onto itself. So to determine what type of loop it is, you say, okay, my investment goes up, therefore productivity goes up, profit goes up, and then investment will go up more. Starting with up and you're ending up with more, that's meaning reinforcing loop. So that can keep on going forever. However, if productivity go up, your resource use goes up as well. If resource use goes up, your resource constraints increase. If resource constraints increase, your productivity goes down. You start with up, you end it with down. So that meaning balancing loop. And that is working against it. And these two loops working against each other. And that is where the dynamics comes from within your system. Identifying these polarities are important. I will show you a diagram later. And to get them right is also important. A trick to do that is to count the number of negatives in the loop. If the number of negatives are odd, meaning 1, 3, 5, then it's a balancing loop. If the number of negatives are even, like 0, 2, 4, 8, 6, then it will be a reinforcing loop because the minuses cancel each other out. It's like in mathematics, you do multiplication. You multiply once by a minus, it makes it a minus. And then your final result will be a minus as well. Yes, so this is what you build up your whole diagram going through this. Also, you need to look at your delays. That is a killer within the system. Things don't happen naturally, always everything happens immediately. Sometimes there are relationships that takes time, a longer time than the overall time horizon of the rest of the diagram that might occur. Because new orders will not immediately increase your production output because it takes time to install new equipment, get new people. It takes time to ramp up. Also, pollutants will take time to contaminate the groundwater because it takes time to siphon down through all the soil. And the delays are shown with these double stripes over that specific link. Okay, so why is this important? If you look at the typical behaviors we see in systems, is if you have one reinforcing loop, it is just running away, it's leading to exponential growth. So the thing in your system that you measures will go up exponentially. If it's a balancing loop, it will come down to a goal that you have set for your system. The key thing is if you start combining them, you can get something like an S-shaped growth, where initially your reinforcing loop is working very strong and you're getting an exponential growth. Normally there's a bit of a delay, and then your balancing loop starts getting stronger and stronger, and your reinforcing loop getting weaker, and you are tapering off, and you then get an S-shaped curve. This is typically your technology absorption type graphs that you get. If you have a balancing loop with a delay, then you can get oscillations. If you have a combination of a reinforcing loop with a balancing loop with a delay, you can get your growth and overshoot and an oscillation. And if you have a reinforcing with a balancing, leading to a balancing and then to another reinforcing in the opposite direction, then you can have a overshoot and collapse type behavior. So these are the things that you can see occur within a situation, and then you can have a gut feel on what type of forces are within it. Or when you have your loops identified, then you can get a feel or idea what type of behavior could be expected from the system. So here is an example I found on the food, energy, water nexus in terms of a causal loop diagram, where you can see you have your water elements here, you have your food elements here, and your energy here, and then there are some other economic type subsystems and the environment type subsystems as well, and how they influence each other. You can see there are many minuses and pluses, and this thing is very difficult to understand, to follow exactly what's going on. It takes time to build this, and it takes time to test and validate this as well. Just as a disclaimer, I have limited research done on the food, energy, water nexus. I have one or two students that have dabbled in it a bit, but the work that I show here is what I found in preparation for this presentation on where systems thinking is applied to help you understand the food, energy, water nexus a bit better. Good, and now the fun starts. You have mapped the system, you looked at the feedback loops, and you have a fair idea about the behavior, and now you can get to the proper system dynamics, which are your stock and flow simulations. That takes your mapping, where you have identified the feedback loops, you start building your model, where you have stock and flow simulations, where you can actually test with simulation what impact your intervention will have over time. So you have something to measure against when you apply it, and you can compare different solutions, maybe trade-offs between different policy decisions. You can test to see what the impacts can be to get the more suited one. So system dynamics was developed by Jay Forrester back in the 50s and 60s. He's quite a remarkable guy. I had a session earlier this week about his life and history. He was in the Second World War on a ship fixing the radar system for the Americans, and he learned all these feedback theories. There was a damping system on the radar on one of the big aircraft carriers. And he used his knowledge on oscillations and feedback within electronic systems to apply that to social systems and social theory. And that gave rise to development of causal loop diagrams and stock and flow diagrams. So what is it? System dynamics can be summarized as it's a qualitative top-down modeling approach that you can do quantitative simulations with. You take the qualitative data that you've captured from your mental stakeholders and you combine that with, for the structure of the system, you can combine that with observed data behavior from your system, and then to start simulating with it. You can do over time, you can see if you can repeat the patterns that have occurred, and you can make changes to see what other patterns may occur due to the structure of your system into the future. And you can see these are stock and flow diagrams, and they are interlinked between the different elements within your system, like your energy, food, and water. But what is stock and flow? It's easiest explained by a bathtub with a tap and a drain. This is typically how it is drawn within your software tools, where you have a stock. It is something that you can measure, that you can have a snapshot to see how much I have in the system. There's a flow in it that happens over time, and there's an outflow that also happens over time. You can have constants that influences the flow. The level of the stock can influence the flow, and you can also have variables that identify the flow. Often, these elements are elements within your causal loop diagram, and you can see how they influence each other. So in reality, your stock is an integral of your initial stock and the integral over time of your inflow minus your outflow. And the key thing is here also that stock don't change instantaneously. When you pull out the plug, your bathtub isn't suddenly empty. It empties over time at a rate. And this is a cause of inertia within many systems. That's why when you change something, the behavior is not immediately visible that you want to achieve. For a very popular example is like the population type simulation with rabbits, where rabbits are increased by births and they are decreased the population by predation or just natural deaths. So the more rabbits you have, the more births there will be. If there's more rabbits, more of them will die as well. So this is a very basic example of it. But you can increase the complexity to look at your typical predator-prey model, where you have two stocks, like foxes and rabbits, where their stocks influences the inflow and outflow of it. Also interesting to note, you can draw that as a causal loop diagram as well. So this is a balancing loop with a delay, because your rabbits doesn't immediately change the number of foxes. It takes place over time. So initially you start off with a few rabbits with lots of grass and food for them around. And suddenly there's a lot of rabbits and a few foxes. And because there's so many rabbits, your foxes population grows a lot until there's too many foxes and they kill all the rabbits. And when there's not enough food anymore, then the foxes start dying off because the foxes can't eat the grass. Eventually, because there are fewer foxes, the rabbits start growing again. So it's an oscillation repeating over and over. And then you can see what's a typical behavior over time of the foxes population from this type of diagram. Using this principle, you can build it for food, energy, water type systems. This is a stock and flow for your water part of it. Although only water part of it is shown here, there are variables like those that are actually linked to the other diagrams. They are just split up for convenience. When you simulate this, you can get your behavior over time of your water system, or let's call it water security is one of the variables they have in there. You can simulate over time what the behavior will be when you have different policies, and the policies are levers that you change some of these variables or constants that you have within a system, and what effect they will have over a long time due to the structure of your system. So this part is only for your water. This one is for the energy sources, and this part is for the food over time. And different policies might have not necessarily the same for all of them. One policy that supports food might be very detrimental to water, for instance. And here is another example, and you can see these models can get very complex very quickly. For the city of Cape Town, it was actually looking at the water levels of the city of Cape Town, but they considered the whole food, energy, water nexus. This is the causal loop diagram they built, and these are the different stock and flow models that are interconnected that is used to simulate what the effect on the water level will be in Cape Town over time, and what impact the different decisions might have on them. So this is basically what I have on systems thinking. So systems thinking is very strong around building models. However, a very important aspect to understand is that all models are wrong. Because any model that you have is a compression or an abstraction of reality. It is not a real system itself. And that is a very dangerous thing to do in complex systems. Because for a complex system to really accurately model a complex system, the only accurate model is the system itself. So when you model it, you have information loss and you don't have the full accuracy. However, one of our slogans in system dynamics is all models are wrong, but some are useful. So we want useful models, something that is not the truth, but it fits the purpose. It helps me answer the question or solve the problem that I want to solve. It gives you the required or the dominant or the most important information to help you solve it, provide explanation and learning, and to help you make a better decision under uncertainty. Because if you compare a city with a map, this is a metro map of a city. So the most accurate model of this city is a city itself. However, this metro map will help me get from the city center to the airport, because that's my objective. So you must know what are the assumptions in your model and what you want to use it for, and what are the answers that you can provide using your model. And you do not necessarily provide all the answers to all different aspects of the problem, just the ones that you've modeled it for. And that is one of the important aspects that you need to consider. Okay, now the final part, I see I'm quickly running out of time. Please stop me if you want, but I'm getting closer to the end. Is what does AI do for us? In the last year or so, it's been getting more and more prominent within our environment. So what I did was I mapped for the different stages of my process, what type of AI can be applied and for what for each of them. Currently, personally, I've only used more generative AI and LLMs to help me with problem framing, mapping the system, identifying elements, and also giving me feedback on my system. Okay, I can also identify the feedback, but when I've developed a diagram to tell me what my drawing is saying, to maybe find gaps and maybe get an explanation of what I've drawn. If in my environment, not really a lot of other AI tools that have been used, but let's look in a bit more detail. If you look at the LLMs, they are much more useful in the beginning part, from framing the problem, processing data, extracting key information, extracting themes. This includes natural language processing. It can help you identify your elements, and also basic feedback. And also, for your learning, you can query the data you have to give you the lessons learned type information from it as well. If you look predictive machine learning, that can help you, especially in the beginning part where you need to get your behavior over time of your system. What are the patterns that can help you with that? It can help you maybe do clustering of certain variables and elements within your system before you start identifying the rest of them. It can also help you with your intervention design. It can help you predict your outcomes. Some of your system dynamics modeling tools like IC Stellar's got an AI capability within it to help you develop the model, can help you test the model, and it can also help you run multiple scenarios, develop scenarios for you to run with it, and to get aggregate results with it. Optimization AIs also have a role to play, although I have no experience with them, but it helps you identifying the key elements within it, but also mostly I would say put that here with the intervention design. Just maybe a point here, just to stand still for a while. If you talk complex systems and complex problems, then optimization is a ugly word. We don't want optimization. An optimized system, optimized policy is not necessarily resilient. And it actually makes you fragile when things change and the optimization then falls flat. And often you don't know, is your optimization at a local minimum or at a best place. So for us in systems approaches, mostly we talk about, it's more balancing, understanding the problem and having robust or resilient policies in place that can adapt over time. You would rather want flexibility and adaptability than a finely tuned and balanced system. Then the other one that I have, okay, it's the same goes for reinforcement learning. It helps you identify the key elements within it until you start modeling it. And also when you're doing this analysis and evaluations of your various solutions that you've developed. And also digital twins is something that's very prominent nowadays. They are most keen here, but you're having done this, being an iterative sequence, it does support you to understand your problem, identifying the elements that are important, and also do your feedback analysis. That's what your digital twins can provide confirmation if you're addressing the right stuff within your system. Okay, just as my voice is dying out, as a summary of my talk, is for the food, energy, water nexus, your systems thinking, help you frame the problem, map the system, and analyze the feedback to get interventions or policies that hopefully is robust and resilient and adaptable to get a resilient system. And AI can help you working with your data integration, pattern detection, with the forecasting and scenario testing with of your policies that you have. And not necessarily optimizing, but getting a good decision at the end of the day. That is steering the system in the right direction, but leave you the leeway to be flexible to adjust for future changes or black swan events that can happen in the environment. The key thing is you want better formed decisions by comparing policies to have understand the risk and increase the resilience of your system. Good. So there are two ways to go about this. You can either be a system dynamicist that you have at the end there, or you can just be a skilled systems thinker. Both of them get to a similar, well, get to an answer at the end of the day. This might be more accurate, but this one might be in time. Thank you.
Thank you very much, Prof. It's been a very insightful presentation. And I think I'm beginning to rethink a niche for myself in this space. Thank you very much for your wonderful presentation. I would give room for colleagues to ask questions. Colleagues, please, if you do have questions for Prof, could you please signify so that we take our questions in an orderly manner?
Oops.
Do we have questions for Prof? Okay, we have
Confused
one
everybody.
hand. Prof, please, you have the floor. Please, you can unmute yourself and speak.
Thank you very much, Prof, for that very wonderful presentation. It brought a lot of theoretical heft to some of the things that we do, I would say, inadvertently. We do not necessarily know we use, right?
Mm.
But my question is, our center focuses on cyber-physical systems, right? And then within from my understanding, within these systems engineering domain, cyber-physical systems would give you the technical foundation or substrate, like your sensors, the control systems and the rest. Then systems thinking will give you the analytical lens, to understand how these interactions occur within the food, energy, water nexus once they are actually deployed. So my question now would be from your experience, right? Given the tools you listed, Iceberg, cybernetics, something like that. How do you decide which one to reach for first, right, on a given problem? Do you have a decision heuristic that you basically, almost like in a combinatorial form, use, or is it mostly intuition, built from experience, meaning that as you get better at it, you now know which tools, which system dynamics tools, which methods do you need to, which system thinking tools do you need to use? My point is, because you mentioned that the famous quote again from Mr. Box, all models are wrong, but some are useful, because how, and I think it's quite possible that a tool can actively mislead someone and not just fail to help, or can actively produce the wrong conclusion. So how do you know which first tool to use on a given problem? Then let me quickly ask all my questions so that other people can have the chance. Then the second one is based on your experience with in Africa, right? Africa is a unique systems engineering case, right? Which systems archetype do you normally advise, or do you normally see used most often in the African context? Yeah.
Okay, they are good questions. I just need to stop this thing. I want to. Oh. Okay, I want to get out. Okay, I'm going to go to my presentation to jump around quicker. Good question. I'm going to answer the first one. There's a long and a short answer about which tools to use. I think the first answer is to use the ones you know. But don't be scared to learn new tools. I think maybe it's a bit more better to maybe look back. The thing is, you want to frame a problem. There are many ways to frame a problem. And I think the more tools you know, the ones you can pick. Otherwise, you have a hammer and you apply to all your tools. So there are different tools for systems mapping. There are different tools for your feedback analysis. You must actually look at what is the type of complexity in the environment. We are actually, and it's the thing that's coming out soon, as part of the Complex Systems Working Group, we are providing a guideline, a field guide on how to select a different or select between different approaches like systems engineering, model-based systems engineering, systems dynamics, and many others, or project management approaches, depending on where the complexity lies in your problem, what type of culture is in your organization, and what type of perspective you will have in your problem. There you look at Michael Jackson's 5 perspectives. So we are looking at something like a heat map, where you map where your complexity lies. Is your complexity in your organization, in the technology, or in environment, or what type of complexity it is? Is it unfamiliarity, or is it constraints? And we are still, that's a work in progress. But as long as you think of something to do your mapping with it, there are many ways to do, for instance, systems mapping, like system dynamics, concept mapping. You can use causal loops to do your system mapping. There are system engineering tools for that. So it is, I think the first approach is to look at maybe what you want to achieve and then pick a tool for you. And if you have a tool that is flexible, you can apply it in multiple aspects of it. The process of what you want to achieve with it. I think that's an easier answer, but the more complicated answer is if you know many tools, then look at where your complexity lies and knows what are the strong and weak points and focus areas of the tool that you want to apply. That was the first question. The second one, you're talking archetype. Yes, I know archetypes. I haven't presented them here. It is difficult to say which archetype is relevant to your food energy mix. Is it ones that come to mind immediately is something like your tragedy of the commons, or your growth and underinvestment, if I can remember the name correctly. But the key thing here is, depending on what your focus on your problem is, even is it within a food, energy, water mix nexus analysis, there might be more than one of those archetypes visible. It can be just a simple fixes that fail archetype at a certain level. If you dive a little bit deeper, it might be shifting the burden. Or if you want to look at the competition between the different nexus elements, then might be escalation, because they start competing against each other. So it's very difficult to say which archetype is the best. or the most suited. I think when you start drawing your causal loops, that you see which loop sits where, then you can start doing a mapping to what type of archetype might be relevant for you there. Or depending on what your perspective on the story is going to be as well. So that's a very difficult one to answer in that style. I think you had 3 questions. Does I answer your question? Or what's the other one?
Yes, you did that. I had 2. Let me just ask 2 more now. Okay, if you don't mind. You mentioned now that optimization is not necessarily the goal, right? From a systems thinking perspective. You never can effectively optimize, and you never know what is truly optimal. But and I think it ties to your point about resilience, being now that resilience the system might need to recover and not necessarily get back to its prior state, right? But from folks in the optimization community would argue that you have approaches like model predictive control, right, that can in a sense absorb robustness, or that cater for robustness, and then introducing shocks into the system. What would you say to that, right? Then my final question, this is final, I promise, has to do with from our research, we are discovering now that the problems are not necessarily technical, right? The socioeconomic aspects are really quite important. Then, for instance, you have so many models. If you look at the water crisis in Cape Town, the electricity problems in South Africa, you had many models that predicted that this crisis was going to happen, and the years it was going to actually be critical, the years that were going to be critical. But there was a lack of corresponding action, right, by the relevant folks that needed to have taken action. And that's often it's not a technical problem, it's more of a socioeconomic problem, right? So how does systems thinking and do that? What's the best approach to factor that in our modeling?
Okay, good questions. Okay, the first one, optimization. I must say that systems thinking is not okay. My comment about optimization is more from a complex systems perspective. It's one of the heuristics. You want flexibility. Even if your system is inefficient, that inefficiency in your system is actually the one that's going to give you the resilience to survive the disturbances or the events that happen, or the things you cannot foresee will be happening. So you carry the cost of having that inefficiency, but that is your safety. And to try and optimize that out is dangerous in terms of complex systems. And that's not necessarily to do with that complex, that systems thinking sake optimization is bad. It's just from a complex systems engineering perspective. You need that little bit of fat, even if it's not optimal, but it will help you survive when things go bad. With all, I must say, things might change, especially with AI and optimal control and balancing, that can make decisions quicker. But the key thing is the delays in the system. When you make those changes or make those adaptations to the system, will the system behave quick enough to adapt to those changes? I think the key thing here is rather to make sure you have the adaptability within your system to quickly change to handle those restrictions if you want to really optimize and fine-tune it and save costs. I think it's a balance. In my perspective, I would say you need to get the balance right within your system. The other one on, yes, like the getting people to listen to you. Another sad example is that Eskom is the leader in South Africa on systems thinking and system dynamics. They have a whole section in Eskom using system dynamics, and they have the top people in the country in that section, but it doesn't say the top management's listening to them. So that what happened in Cape Town is, or happen in other organizations, even if you have the best answers, doesn't really help if those in command or in control of it listen to you and make the right decisions. Then it's a waste of time. I think the way around that maybe is education. You need to get your top management, knowledgeable in systems and systems thinking, and that is something that's happening nowadays. The topic of systems thinking is growing in importance really in the country, and more people are talking around it. More people are doing the courses. I think that is a key thing. We need to teach people, and that needs to start at school level, getting school people to think and talk and model in systems. I think that is a key aspect there. I don't know if that answers your questions.
No, it does. There are no easy answers, but I think
never. If it was easy, somebody else would have figured it out a long time ago. Then we
exactly.
Yes.
No, and it's also a problem in general in academia. That's why they often tell you to try to start going into policy briefs, write policy briefs, write op-eds in a bid to, leverage on the education that you mentioned. So I think, that's often the first start. Thank you so much, Prof. Very insightful. Thank you.
Okay.
All right. Thank you very much, Prof.
But feel free if there's further questions. Do you want to discuss things? Anybody? I have an open email policy, open door policy.
Thank you very much, Prof, for that opportunity. I think we'll take one other question from Dr. Oliver. Dr. Oliver, please, you have the floor.
Okay, thank you so much, Prof, for your nice presentation. This is an insight in our studies. Presently, most of the researchers here are going through the process. So from system thinking, you have presented today, we have food, energy, and water. So my question now is, when the system wants to when the system wants to think from food, energy, is there any order, picking food first, water and energy, or water, energy, and food, or energy, food, and water? So does the order really matters? That is my first question. The second one is that in Africa, for instance, we may have food, energy, water ecosystem in Africa. Do you think that Africa has preference other than other developed countries like Europe or US? Or what do you think that we can do in Africa to make food, energy, water nexus interesting? Thank you so much.
Okay, good question. I'm going to give you the answer that I used to give all my difficult questions in systems engineering and systems thinking. The answer starts with, it depends. I wouldn't really say there's one that's more important than the other. It depends on what's your focus. What is the purpose of your investigation? If you, like for instance, the one that I have here from Cape Town, the focus there is they want to look at the water levels, but they want to look at the water levels of Cape Town reservoirs in the context of the food, energy, water nexus. So obviously, I think they will start with water. If you want, it depends also on what level you want to work at. If you want to work at a very high level, you can look at everything together. But if you go down into the weeds and the nitty-gritty, you have to pick a place to start. And that will depend on what you want to achieve. I can't really say which one is better than the others. It really depends on where the problem lies, where you want to start, what you want to achieve with it. Like with systems thinking, there's never really a right or a wrong answer, but some are better than others. And I think it also comes down to experience, knowing after you've done it a number of times, you get better with the tools and the approach. You can start with everything at once, or you can then focus on one. So there's no really easy answer on this. I think the key thing is at the end of the day, as long as you consider all important impacts to your system, and that also comes to where you pull your boundary and where you lay your focus. So there's no really easy answer to this.
Thank you very much, Prof.
Some people will start with the energy first, and then they look at all the other stuff and they think that's peripheral. Everybody think his field is the most important. Sorry.
All right. Thank you so much, Prof, for that answer. Before we go, do we have any more questions for Prof? All right, so I want to believe that colleagues will take advantage of the open email policy that Prof has given us. So I believe that probably after we've gone through the section again, we would be free to reach out to Prof to gain more insights and ask further questions. On behalf of our director, Professor Nnamdi Nwulu, I would like to extend our sincere gratitude to Professor Rudolph for this very insightful presentation. This presentation has opened our eyes, in particularly myself, on some of the niche areas where we can pitch our tent as water, energy, and food researchers. And I believe this has also helped colleagues also to clarify certain concepts and also provide more information on our research areas. So I want to appreciate you kindly for this opportunity and for the presentation. Thank you very much, Prof. And thank you, colleagues, for joining this presentation. In the absence of any other questions and comments, I would like us to end the presentation or the meeting. Thank you so much, Prof, for joining. Thank you, colleagues, for joining.
Thank you for having me. It was fun. Thanks. Bye.
Thank you.
Thank you, everyone. Bye-bye.
Thank you, colleagues. Have a great day ahead.
Thank you.